Okay, so I'm just checking if you can see my slides.
Yes, I can see your slide.
Perfect, thank you. So good afternoon, everyone, and welcome to this session. I'm so happy to be able to present to you today. So in this session, we'll be looking at some fundamental features of meta-analysis, and these will help you to interpret any meta-analyses that you may come across, and also enable you to make informed decisions when conducting your own meta-analyses. Things we'll be covering in the session are when it will be appropriate to conduct a meta-analysis, how to interpret the data presented in forest plots. We will look at the differences between fixed effects and random effects models, and we will look at how to identify heterogeneity and appropriately account for it during analysis. We are all familiar with designing a study and collecting the appropriate data for our outcome, and then calculating an effect estimate, which could be a risk ratio or odds ratio or mean difference, to name a few. And there could be several studies that looked at the same outcome as us and are interested in the same data as us. And they could have found either the same results as us or differing results. For a review, we are interested in bringing the results of these studies together. And one of the ways we can do that is with a meta-analysis. So what is a meta-analysis? A good way to indicate this is a fun little activity where we have three statements. So we have A, B, and C. And each statement either relates to the meta-analysis or not. So you can type it into the chat, which of these statements you think are correct for a meta-analysis. It could be one or all, or it could be none. So our first statement A is a meta-analysis combines the results of individual studies to estimate a common effect. B, a meta-analysis can make sense of a contrasting body of evidence. Or C, all systematic reviews are meta-analyses. So just type into the chat A, B, or C, which statement you think is true.
Yeah, a couple of A's coming through.
Okay.
A and B are true. C, A. Almost everyone is saying A.
Okay, great. So A, the first statement, a meta-analysis combines the results of individual studies to estimate a common effect. This is technically false. So the key word that's missing that makes this statement true is the word statistically. So a meta-analysis statistically combines the results. So it uses statistical methods to come up with a common effect estimate. Another way of combining results could be narratively or vote counting. So what sets meta-analysis apart is that it uses statistical methods. B, a meta-analysis can make sense of a contrasting body of evidence. This is true, as we saw in the previous slide. So if the individual studies are giving us conflicting answers, a meta-analysis may settle the controversy by giving us an overall answer. And if we use a forest plot and examine the heterogeneity, we may be able to understand where these differences lie. And C, all systematic reviews are meta-analyses. So this is indeed false. A meta-analysis is an aspect or a part of a systematic review, and it may or may not be present. So not all studies are able to be statistically combined, and this may be due to missing data, or maybe the studies are too different to be combined. We have two more statements, which you can type into the chat whether you think it's true or false. So we have D. A meta-analysis increases the power to detect differences by increasing the sample size. And E, all meta-analyses are systematic reviews. You can type in either D or E or both if you think they're both true into the chat.
D. So they're saying D is true. One says both is true. One is saying E is true. Mostly D's, Yusentha.
Thanks, Solange. That's wonderful. So D is in fact true and E is in fact false. So a meta-analysis increases the power to detect differences by increasing the sample size. This is correct because by combining the samples we have from the different studies, we're increasing our sample size, thus we're increasing our power to detect differences. And this also increases the precision in our answer or our confidence in the answer. And E, all meta-analyses are systematic reviews. This is false. A meta-analysis can be presented with or without a systematic review. So you can meta-analyze any studies outside of the review environment, but you have to keep in mind that the included studies may not have underwent the rigorous process that a systematic review follows. So in summary, a meta-analysis statistically combines the results from 2 or more studies to estimate an average or a common effect. And it's usually seen as part of a systematic review, but not all systematic reviews have a meta-analysis, and a meta-analysis can be done as a study on its own. Maybe, Solange, are there any questions? Or if there's any questions, feel free to pop it into the chat at this
None
point.
yet. None yet. I'll
Okay.
let you know.
Thanks, Solange. So the next thing we're going to look at is when is it appropriate to conduct a meta-analysis? So again, we're going to have a couple of scenarios, and you can type in either A or B if you think a meta-analysis would be appropriate for that scenario. So we have scenario A. We have one study investigating physical activity for smoking cessation. And scenario B, where we have 12 studies from 8 different countries, and they investigated the effect of formula versus breast milk on weight gain in preterm and low birth weight infants. So for which of these scenarios would meta-analysis be appropriate?
Mostly B's coming through. Yes, majority. Almost everything is B.
That's excellent. So for scenario A, a meta-analysis is not appropriate because we need at least 2 studies to be able to meta-analyze, but you can include one study in a systematic review. And B, so meta-analysis is appropriate for this. If the PICO of the studies, if you're not familiar with PICO, that would be if the participants, the interventions, the comparators, and the outcomes are similar enough across the studies, then they can be meta-analyzed, regardless if they are from different countries. And next 2 scenarios, so we have C and D. C, 13 studies fulfill our PICO criteria. 9 of the studies are at high risk of bias. And D, 9 studies investigate the effect of total knee replacement. 5 of them use a tool that evaluates pain, and 4 of them use a tool that evaluates pain and physical function. So which of these scenarios would meta-analysis be appropriate for?
Yusentha, there is a question in the chat, so asking what PICO is.
Oh, okay. So PICO stands for participants, intervention, your control or comparator, and your outcome. And it's a way to summarize the research question when you're doing systematic reviews.
So quite a few people are saying both, and then a few D's and C's. Mostly both.
Okay.
One says neither.
That one is correct. So it would be neither. So C, 13 studies fulfill our PICO criteria. So that means the research question was similar across all the studies, and it looked at the outcomes, the participants, the interventions, the comparators, and the outcomes that we're interested in. And 9 of them were at high risk of bias. So if most of the studies are biased, then the result of the meta-analysis may also be wrong. And if you meta-analyze biased results, then you increase their precision, you narrow the confidence intervals, and you increase the people's confidence in the result. And it will give the results more credibility by labeling them as a systematic review. So it would not be appropriate in this case. For D, 9 of the studies 5 of them evaluate pain and 4 evaluate pain and physical function. So these scales are not really measuring the same thing. One is measuring pain while the other is measuring pain and physical function. So the results should not be combined. But you can, however, meta-analyze the 5 studies that measure pain separately from the 4 studies that measure pain and physical function. So it's up to you to use your judgment to decide when measures are similar enough to be combined and when it will give a meaningful answer to your review. And the last scenario, so E, 15 studies investigate the effect of physical activity on stress reduction. The interventions studied are swimming, jogging, dancing, yoga, and hiking. So would meta-analysis be appropriate in this case? Type in yes or no in the chat.
Yes. 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 Yes.
Okay.
So everyone is saying yes.
Okay, well, half right. So it does depend. So in some cases, it might make sense to combine a broad range of studies. So for example, if your objective is to investigate the impact of exercise versus no exercise, then you might be happy to include many different kinds of exercise programs. And you would get a broad answer of the effectiveness. On the other hand, it may be too broad to be useful. So this would not answer questions between the differences of, say, swimming and jogging, or between long exercise programs and short exercise programs. So if your aim is to get a specific answer for specific exercise program, then you may want to break up your review into several separate meta-analyses. And again, it's up to you to make those judgments on the aim of your study. So we saw the situations in which doing a meta-analysis is not advised. The first is where we are mixing apples with oranges. So that is when the studies are too different to be combined. And it would not make sense if we combine their results. So before we combine it, we need to make sure that they're comparing the same interventions and that they're measuring the same outcomes. And you'll need to use your judgment to decide when this is the case. In some cases, it might make sense to combine a broad range of studies. And on the other hand, the answer may be meaningless and genuine effects may be obscured if the studies are too diverse. The second reason why we may not want to do a meta-analysis is if the studies are too unreliable. So that is if their risk of bias is too high for us to be confident that they are telling us the truth. A meta-analysis is only as good as the studies in it. So if the studies are biased, then the result of the meta-analysis will also be biased. It's also important to consider whether your studies are a true reflection of the research in the field. Reporting bias or publication bias might mean we have an unrepresentative sample, and that exaggerates the true intervention effect. So if you suspect that your review is suffering from this problem, it may be best not to present a meta-analyzed result. So if you, yes, Solange.
There's a question that asking about whether the study methodology matter.
Yes. It will come in under heterogeneity. So it does affect that. But in general, at the beginning of your systematic review, you would state what kind of studies you're looking at. But definitely study methodology does play a part in whether meta-analysis result is reliable or not. Later on in the presentation, I'll show you this as well. Okay. So if you are confident that you have a group of studies that are sufficiently comparable and reliable, then we can go ahead and we can meta-analyze these studies. And to do this, we need to have at least 2 studies measuring the same thing in a similar way, and we need to have the data in a format we can use. And for example, if it's a dichotomous outcome that we're looking at, so a yes-no, then we need to know the number of events that occurred and the number of people in each arm. And if it's a continuous outcome that we're looking at, we'll need to know the mean, the standard deviation, and the number of people in each group. Okay. Solange, are there any questions so far?
There's a question from Anati who's asking if you can do a meta-analysis without doing a systematic review first. And there's a question from Cecilia on whether meta-analysis can only be conducted with interventional studies.
Okay, so for the first question, you can do a meta-analysis without a systematic review. So if you find the same thing that you're interested in and you wish to estimate a common effect, then you can do a meta-analysis on it. The difference with the systematic review is it undergoes a rigorous process. So it ensures that all your inclusion criteria are met, your exclusion criteria. It also analyzes the risk of bias. Though there are tools that you can use as well, but it doesn't need to be in the environment of a systematic review. So it can be a study on its own. And the second question, sorry, Solange, can you repeat that, please?
Sure. Does it mean that meta-analysis can only be conducted with interventional studies?
No, so it can be done with prevalence studies as well. Other effect estimates you can use are the correlation as well. So there are correlational studies that you can include in a meta-analysis.
Thanks. No more questions for now.
Thanks, Solange. So the next thing we're going to look at is how to read a forest plot. So the results of a meta-analysis are presented on a forest plot, and it's called that because it's said to resemble a forest of lines on the page. So each row of the forest plot represents a study in the analysis. So in this example, we have 4 studies. So this review is looking at the impact of statin dose on death and myocardial infarction. And this review found 4 studies applicable. So we have the Prove It study, A to Z, TNT, and the Ideal study. The effect size or effect measure is the value that reflects the strength of the relationship between the intervention and the outcome. So for example, you can have an odds ratio or mean difference, but in this case, we have a risk ratio. And it's represented by a square on the forest plot. So the location indicates the direction and the magnitude of the effect. So for example, you have the Prove It study, which found a risk ratio of 0.84, and TNT study, which found a risk ratio of 0.8. And you can see this corresponds with the scale on the bottom. And of the 4 studies, we can see that they all favored a high dose, a high statin dose. The effect size is bounded by a confidence interval, and this reflects the precision with which it has been estimated in a study. So the narrower the bands, the greater the precision. If we have a look at the 4 studies, we see that the Ideal study had the narrowest bands, and thus it had the greatest precision. The Prove It study, however, its bands are quite wide, so it had the least precision of the 4 studies. You'll also notice that the size of the squares vary, and this is to reflect the weight assigned to that particular study. So how important that study is to the analysis, how much it contributed to the final summary effect. So the studies with good precision will be assigned more weight. So since the Ideal study had the best precision, it was assigned the highest weight of 37%, and you can see that the square was largest for the study. Prove It study, which had the least precision, was assigned the lowest weight of 13%. The p-value will fall under 0.05 if the 95% confidence interval does not include the null value. So for a risk ratio, the null value is 1, And if we scan the confidence intervals, we can see which studies were statistically significant and which were not. So of the 4 studies, 3 of them include the null value. Only one does not. So that means TNT was a statistically significant study. And if we have a look at the p-value, this confirms it. The only statistically significant result was for TNT. And finally, we have the summary effect. And this is represented by the diamond and is simply the weighted mean of the individual effects. So the location and the width represents the effect size. The actual risk ratio of our summary effect is 0.85, and the precision is 0.79 to 0.92. So that means based on all of these studies, the actual impact of statin dose on death and myocardial infarction is likely to fall somewhere within this range of 0.79 to 0.92. If we have a look at the diamond, it does not include the null value. So that means it is a statistically significant result. So there is a difference between the intervention and the control. And if we have a look at the p-value, this also confirms it as well. Are there any questions about the forest plots?
There is a question from Aslam about whether there are factors other than precision that contribute to the weight.
No. No, so it's only the precision that contributes to the weight. Okay.
No other questions.
Okay, thanks, Solange.
Sorry, Yusentha, don't the number of events also count?
Well, I guess in a way, so the weight is directly calculated using just the variance. So if there are a few number of events, the variance would be wider. So I guess indirectly.
Okay.
But according to the model and the formulas, the weights depend only on the variance in the study.
Okay. Thank you. There is a question from also Sunday's saying that the interpretation of the forest plot is still not clear. And then Brian is asking, how do you calculate precision?
Okay, so there'll be examples at the end where I'll go through a forest plot again, and maybe it'll be more clear then. And how to calculate precision. So precision is based on your confidence interval and your standard error. So you calculate the standard error within the study, and that gives you your 95% confidence interval. And this is based on the variance found in the study. So remember, in each study, you present an effect estimate with a confidence interval, and the confidence interval is what we refer to as the precision. And narrow confidence interval means greater precision. Okay. The next thing we can look at is the fixed effect versus the random effects model. So to begin, let's assume that Alice conducts a study among 300 participants from Cape Town to study the effect of a drug on managing blood pressure. And she gets a particular risk ratio. Let's also assume that Ben conducts the same study in Cape Town, but with a different group of participants, and he gets a particular risk ratio. Would you expect the risk ratios to be the same or similar or completely different? Maybe you can type it into the chat. Do you think it would be the same, similar, or completely different?
So Sunday says similar, similar, similar. Brian doesn't know. Similar. It seems that most people think the same.
Okay, so that's great. So the results, it's unlikely that the risk ratios will be exactly the same since different participants are used in the studies, but you would expect the risk ratios to be similar since it is the same population. So the risk ratio that Alice finds and the risk ratio that Ben finds is what is called the observed effect. So it's the effect that they actually find in the study. But there is an underlying effect that we know really exists, and this is called the true effect. And we would only know the true effect of the blood pressure drug if we could measure everyone in Cape Town. And Alice and Ben are both trying to estimate this true effect by doing samples. So if Colin conducts the same study in Johannesburg, what do you think about his risk ratio? Would it be the same, similar, or completely different from Alice and Ben's?
I'm getting different. It'll be different from most people.
That's correct.
Gina says, depends how different the Johannesburg population is.
True as
There's
well.
a question from Privilege about what determines the risk ratio, but mostly everybody's saying different.
Okay. So the risk ratio is dependent on the number of people. So it is for a dichotomous outcome, so yes and no. So in this case, if the outcome is managing blood pressure and the effect measure is a risk ratio, then perhaps the outcome is you'd be interested in knowing the number of people who have whose blood pressure maybe has decreased or is managed, sorry, number of people whose blood pressure has been managed versus the number of people whose blood pressure is not under control. And then you would calculate a ratio based on the number of events in each arm. Yes. Okay. So I think Solange said most said that it would be different. So that's right. So if Colin conducts his study in Johannesburg, not only will his risk ratio be different from Alice and Ben, but also the underlying effect or the true effect of his population may also be different. It could be the same, but it could also be different. And this is because we're looking at a different population now. So most meta-analyses are based on one of two statistical models. So a study's true effect is the effect size in the underlying population. So the effect size we would observe if the study had an infinitely large sample size. That means no sampling error. We could measure everyone in the population. And a study's observed effect is the effect size that is actually observed. And how we think about the true effect is what determines whether we use a random or a fixed effects model. So whether we think the true effect would be the same, for instance, between population 1 and population 2, or if we think the true effect will be different for each of these populations. And that is what determines whether we use the fixed effect or the random effects model. So if we assume that there is only one true effect, and the only reason that the observed effects differ is because of sampling differences, then we will use the fixed effects model. We're assuming that all the factors that could influence the effect size are the same in all the studies, and therefore the true effect must be the same for all studies. So in this figure, we have a true effect of 0.6, and this could be any effect measure. It could be a risk ratio, or a mean difference, or odds ratio. So we're assuming that there's a true effect that's applicable for all of these studies of 0.6, and we have 3 studies trying to estimate this. The squares represent the observed effect, and the circles represent the true effect. So study 1 found an observed effect of 0.4, study 2 found an effect of 0.7, and study 3 found an effect of 0.5. So remember that all of these studies are trying to estimate this true effect. And the only reason they haven't exactly estimated it is because they cannot sample everyone in the population. So when we calculate a summary effect in a meta-analysis, we're trying to estimate this common effect size. So we're assuming that all the differences you're seeing between the studies are only due to sampling error. That means it's only due to the fact that we cannot sample everyone in the population. And the weights are assigned with the goal of minimizing this within study error. So these are the formulas for calculating the summary effect, but I won't go into detail because of time, and most software will calculate this for you when you select which model you'd like to use. The most important thing to know here is that the weights are based on the within study variance, which is the standard error squared. Okay, so studies with a large sample size will have better precision. It'll have smaller variance, and so it will be weighted more than a study with a smaller sample size. And this is because we assume that the only reason the observed effects differ is because of sample size and precision. So studies with a smaller sample can largely be ignored since we are getting better information from a larger study about the same true effect size. So the most important thing to know about the fixed effects model is that the weights are assigned with the aim of minimizing only the within study variance. The second model we have is the random effects model. And since the studies will differ in terms of participants and interventions, among other reasons, there may be different true effects sizes underlying the different studies. So the random effects model allows the true effect to vary from studies to study. So in study 1, we see that the true effect for this study was 0.55. And study 1 tried to estimate this using with their study, and they got an observed effect of 0.35. The true effect in study 2 was different, so it was 0.65. And again, study 2 tried to estimate this true effect. And the true effect in study 3 was also different, so it was 0.5. So if it were possible to perform an infinite number of studies, then you would get a range of true effects. And these true effects would have some kind of mean. So when we calculate a summary effect in our meta-analysis, we're now calculating an average of these true effects. So remember before the fixed effects, we were calculating the true effect itself. But now with the random effects model, because we have several different true effects, we now calculate an average of the true effects. So now when we we need to take into account two sources of variance. So firstly, we have the within study variance. So like we saw with the fixed effects model, the reason why we cannot directly estimate the true effect is because of sampling error. And secondly, we have another source of variation, and this is from the studies having different true effects. So now when we weight our studies, we need to minimize both these sources of variance, the within study variance for each study, as well as the variance across studies. This accounts for the studies having different true effects. So now when we're weighting the studies under the random effects model, we can't afford to ignore smaller studies because they may be estimating a true effect that we don't have information about. So our weights have to consider both the within study variance and the between study variance. And you'll see that with the random effects model, the weights are more or less evenly distributed since all the studies are providing valuable information. So just to recap, under a fixed effects model, we can largely ignore the information in the smaller studies since we have better information about the same true effect size in larger studies. And under a random effects model, all the effect sizes need to be represented in the summary estimate. So we cannot discount a small study by giving it a small weight, and likewise with larger studies. So study weights are more balanced. You can see this in the relative weights if you compare it between the fixed effects and the random effects model. So under the fixed effects model, the weights, you'd see like the donut study had 39%, had the highest weight, whereas with the random effects model, they're more or less the same. And you can tell this by the sizes of the squares as well. So under the random effects models, they're more or less balanced. The standard error and the confidence intervals for the summary effect are wider under the random effects model than the fixed effects model. And this is because with the random effects model, we're now trying to estimate a range of true effects. So this confidence interval needs to capture that extra variation. Whereas with the fixed effects model, we're just trying to estimate a single true effect. So since we have many studies talking about the same true effect, trying to estimate the same true effect, then our confidence interval is naturally narrower since we have greater power. The selection of a model must be based solely on the question of which model fits the distribution of the effect sizes. And this depends on what you think of the population. So whether you think that you're likely to find different tree effects or the same tree effects, that is what you base on whether to use a fixed effects model or a random effects model. And when studies are gathered from published literature, then the random effects model is generally a more plausible match. Are there any questions about fixed and random effects models?
Yes, there's a question from Brian, and he's asking, how do you know the true effect in random effects models?
Okay, so we'll never know the true effect, but we're trying to estimate the true effect. So in a random effects model, it's still a weighted average of the true effect. So in this example, we have different true effects, but a weighted average of it would be 0.6. So in our meta-analysis, we would report 0.6 as our combined effect estimate, and it's an estimate of the true effect. So instead of just looking at a single study, we've now amassed all this evidence from different studies, and that gives us better confidence that we're getting close to knowing the true effect. So it is a weighted average of the different observed effects in the study. Are there any other questions?
There is a question from Homa. How did you get this figure? Not exactly sure which figure he's referring to, I think, also because my slides are a bit delayed.
Oh, okay. Well, I can tell you that the figures used are from a textbook. So it's Introduction to Meta-Analysis by Borenstein. I do have it at the end of the slides as a reference, which it's an excellent resource for learning meta-analysis.
Thanks, Yusentha. No other questions.
Okay, thanks, Solange. Okay, so the next thing we're looking at is heterogeneity. So heterogeneity refers to the variation between the results of studies, and we know study results can differ. And this difference, heterogeneity specifically refers to the differences between the true effects being evaluated in the different studies. So more specifically, heterogeneity can be attributed to clinical diversity, methodological diversity, or statistical heterogeneity. Okay, and this is an alternative to homogeneity, where we assume there's identical true effects underlying every study. So the first source of heterogeneity is clinical heterogeneity. If you are familiar with the concept of PICO, so PICO stands for Participants, Interventions, Control, and Outcomes. And it refers to the items that we're interested in our review. So the types of participants we're interested in, the interventions, the control, and the outcomes that we're interested in. So you can use this to help you identify the elements that could contribute to there being differences between the studies. So for example, in your studies, your participants could differ by condition, or age, or gender, location, and study eligibility criteria. So for example, some of the studies that you find could have been done only in males, while other studies could have been done only in females. And this could contribute to the differences you're seeing in the effects. So maybe there's a difference in effects between males and females. Heterogeneity could also arise from differences in interventions. So if the interventions in your studies differ in intensity at dose, duration, maybe the way they were administered, if some interventions had additional components, and also the experience of practitioners. So this could also contribute to the differences you're seeing among studies. The controls could be different. So some studies may have chosen to use a placebo, whereas other studies could have chosen to use no control or just standard care. And the outcomes could also differ between studies. So perhaps the follow-up duration was different in studies, the way they measured it, maybe how they defined an event, or what cutoff points they used. The other source of heterogeneity is methodological heterogeneity. And this can arise from differences in the study design or the study conduct. So with study design, we're looking at either randomized versus non-randomized studies, crossover versus parallel, individual versus cluster randomized. So if you're combining randomized and non-randomized studies, this may be why you're seeing differences in the results. Likewise with crossover and parallel. So you would need to investigate whether this is contributing to the differences or not. And heterogeneity can also arise from the conduct of the study, more specifically the risk of bias. So if some studies are at higher risk of bias than others, that could explain the differences you see. Another item that could contribute to methodological heterogeneity is the approach to the analysis. So perhaps how the study analyzed the results. This is directly speaking to statistical methods used in the paper. And the last one, statistical heterogeneity. So there will always be statistical heterogeneity since studies will have different samples. So statistical heterogeneity refers to the sampling variation. We can look at two statistics to measure heterogeneity. The chi-square test provides a yes or no answer as to whether there is heterogeneity, so whether there's differences between the studies. So it answers the question if are all the studies estimating the same true effect. If the test is significant, so if it's less than 0.05, then we can conclude that there is heterogeneity. However, it can have low power if there are too few studies, or it can be too sensitive if there are outlying studies. So some systematic reviews choose to use a cutoff of 0.1. So if the p-value is less than 0.1, then we can conclude that there is heterogeneity. A more useful statistic is the I-squared statistic. So it's a percentage of the variability due to heterogeneity rather than to chance. So it's low values indicate no or little heterogeneity, and high values indicate a lot of heterogeneity. And roughly speaking, values are above 75% represent high heterogeneity. But both of these tests should be interpreted only as a guide and in conjunction with a visual inspection of the forest plot. So our chi-square test is a yes-no test of whether there's heterogeneity. And our I-squared statistic tells us how much heterogeneity there is. And this can range from 0% to 100%. So we need to look at have a visual inspection of the forest plot to also determine if there is heterogeneity or not. So remember, heterogeneity refers to differences between the studies. So between forest plot A and B, which one shows more heterogeneity? You can type in A or B into the chat.
But mostly B's coming through.
That's great.
Everyone is saying B.
Yes, that's great. So forest plot B, which exhibits the most heterogeneity. Remember, heterogeneity is differences between the results of the studies. So the first step you should always take is to visually examine your forest plots and to look whether all your studies are reporting consistent results. So you need to look for overlap in the confidence intervals and not just whether the blue dots line up, not just whether the actual effect lines up. So for example, in forest plot B, we see that these studies on the left, their confidence intervals don't overlap with some of these other studies. And that's a sign that there may be heterogeneity amongst your studies. So it's not likely that these studies are all measuring the same true effect, in which case a random effects model would be appropriate for this one. So we have some examples that we can look at on interpreting the forest plot and looking at heterogeneity. So here we have a forest plot from looking at stretching to prevent or reduce muscle soreness after exercise. So we have our comparisons as post-exercise stretching, and the outcome is soreness on day 1. So like we saw before, each row represents each of the studies included in our meta-analysis. So we have 4 studies included in this analysis. We have our intervention arm, and we have our control arm and the details of each. So soreness here is measured as a score. So we have a mean score for each study in both the intervention and the control arm. And we have our effect measure being the mean difference. And we also have the weights of the study. If we have a look here, it says that it's using the fixed effects model. So they have reason to believe that all of these studies are trying to estimate a single true effect. If we have a visual inspection of the forest plot, all the confidence intervals overlap, so this is likely to be true. With our weights, so we have our weights for each of the study. We see that for the third study, it was assigned the greatest weight of 45%. And this is likely due to it having the narrowest confidence interval. So meaning it was the most precise study. We have our summary effect calculated here. And this is calculated as minus 1.04. We also see that it crosses the null value here of 0, which means we didn't find a statistically significant result. So we can't conclude that there is a difference between the intervention and the control after considering all of these studies. At the bottom, we have our heterogeneity statistics. So we see we have our chi-squared test and the p-value of 0.97. So since it's greater than 0.05 or 0.1, then you can conclude that there was no evidence of heterogeneity. And we have our I-squared statistic, which is 0%, also indicating no heterogeneity. So all 3 of our statistics, well, 2 statistics and our visual inspection indicate that there's no heterogeneity among these studies. We also have a test for the overall effect. So it gives us a p-value of 0.73, and this tells us whether the overall effect is significant or not. And this also confirms what we saw with the confidence intervals here. We have a second example. So this one is looking at dance movement therapy for depression. And it's using the random effects model. So we see we have 3 studies included here. The outcome is a depression score. So it's measured, so we have a standardized mean difference. And if we have a visual inspection of the effect sizes and the confidence intervals, we see that for study 1 and the last study, study 3, the confidence intervals do not overlap, which indicates that there could be heterogeneity amongst these studies. If we have a look at our heterogeneity statistics with our chi-squared test, we see that the p-value of 0.01, which indicates that yes, there is heterogeneity. And we have our I-squared statistic, which is 76.4%, which indicates there's quite a bit of heterogeneity, so high heterogeneity. So if the studies are too different, we can do a subgroup analysis. So if you find there's high heterogeneity amongst your studies, we can do a subgroup analysis and check if the summary effect changes. So for example, we have a study looking at antibiotics to prevent complications following tooth extractions. So we have they administered an antibiotic and then they compared it to a placebo and the outcome was a pain score. So if we have a look at the total effect, we see that it is not statistically significant. It includes the null. If we look at the test, the p-value for the overall effect, 0.12. So again, it confirms it's not significant. And if we have a look at our heterogeneity, we see that the I-squared statistic is 44%. So there is moderate heterogeneity here. However, if we look at the summary effects within each subgroup, we see that the heterogeneity for preoperative prophylaxis is 0%, and the heterogeneity for pre and post-operative prophylaxis is 0%. So that means that if you consider all the studies together, you would find heterogeneity. However, if you separated it by how the intervention was administered, so whether it was administered preoperatively, postoperatively, or both, then you would find more consistency amongst the results. And in fact, if it was administered at both times, in this case, you find a significant effect. So separating your studies and accounting appropriately for heterogeneity can help you detect differences. So it's always best to have as low heterogeneity as possible. So there are many packages you can use to conduct meta-analysis. You can use a Microsoft Excel by either typing in the formulas or using an add-in such as Meta Essentials, Meta Excel, or Meta Easy. You can use a specific statistical software such as Stata with the Meta command or R with its Meta command. And there are also meta-analysis specific software such as RevMan 5, which is the Cochrane software, and comprehensive meta-analysis. So some resources that you may find that may be helpful are the Cochrane Handbook, the Cochrane Methodology webpage. And you can always refer to YouTube for RevMan and Stata tutorials. And an extremely helpful book in learning meta-analysis is by Borenstein, Hedges, Higgins, and Rothstein. So it's an introduction to meta-analysis. And just to acknowledge that some of the material presented today is based on this book and also on Cochrane training slides. And that brings us to the end of the session on meta-analysis. Thank you so much for your attention. I'm happy to take any questions or comments.
Yusentha, yes, there's one question from Aslam, and he's asking, what is tau?
Oh, okay. So tau squared is the between study variance. So remember, you have two types of variance in a random effects model. You have the within study variance, and that's your standard error. And you also have a between study variance, and that's your tau squared. And that's used to help you calculate the weights in the study. And there are specific formulas to help calculate tau squared. They are outlined in the book, so you can refer to that if you're interested in more details.
Thanks, Yusentha. And then Fayasa asks, does it mean that heterogeneity test is done to decide whether to use fixed or random effects model?
That's a very good question. So to decide whether to use a fixed or random effects model needs to be done generally before you conduct your meta-analysis, and it needs to be decided on using the literature, what you think is appropriate. So whether you think that there'll be different true effects or not. And the heterogeneity statistic should not be used to decide whether you use a fixed or random effects model. You use the heterogeneity statistics to try, and it can help you with your subgroup analysis as well.
Center. Francine is asking about training for Rev 5 manager. Yeah, I think if you can get in touch with us at Cochrane South Africa, we can send you some things on that. I don't think we're planning to do anything specific on RevMan 5 this year, but do get in touch and we can point you to some other training available. And I don't think there's any more questions. There's just people saying thank you, Yusentha, and that the session was very helpful and that it was well presented and well organized and informative. Okay, one last question maybe from Dr. Ogunlana, who says whether you can use SPSS for meta-analyses.
I'm not sure about that. Yeah, maybe we can do a bit of Googling, and yeah, I haven't heard of it, but perhaps a lot of the software are now adding meta-analyses commands. Yeah.
Great. Thank you. So thanks, everyone. We've come to the end of the webinar. Thanks, Yusentha, so much for your presentation, which was very informative and useful to everyone here, according to all the comments, which is great. Jaron is saying that the new SPSS version has it. So I think if you investigate a little bit, you can find out more about that. And thank you, everyone. I've pasted the link to the evaluation of this webinar on the chat. So if you can please complete that, we would really appreciate it because it does inform us about future training and how we should run it and how to run it better. Thank you so much. Thank you, Yusentha, and bye, everyone. And Chipang, do email us separately and we can point you towards other systematic review training. Thanks, everyone.
Thank you. Bye-bye.
Okay.